so now we are going to go over capacitors and the three kind of basic shapes of capacitors you need to be familiar with. The first would be just a parallel plate capacitor. For that, you're going to say that the capacitance is equal to E naught A over the distance between them. Right there. E naught A over the distance between them. Pretty straightforward. Cylindrical capacitors, however. So here's a cylindrical capacitor. Oh, sorry, I might have zoomed in too much. We've got a solid cylinder with a radius A and length L, and surrounded by a shell with radius B. And this is a top view of this. So the electric field lines, again, there's no electric field in here inside the conductor. There's no electric field in this conductor. All the electric field lines just run from here to here. To figure out the capacitance of this, again, capacitance is, there are two formulas. There's E naught A over D, which is for a parallel plate capacitor, but the better way to do it is Q, the total charge, divided by the difference of voltage. So what we really need to do is figure out the difference of voltage between this point and that point, or the difference of potential between these 2 points. And we know that the difference of potential is related to the electric field and the distance between those 2 points. Or that, down here, that the change of potential is equal to negative integral from A to B of the electric field times the distance, like ds. And so see it going up, it's the integral from A to B of the electric field times that distance. That has changed here. They used R instead of S. That's fine because it's a radius, because it's a circular kind of shape. And then this negative 2 Ke lambda over R is the electric field of a cylinder. So let's see if I can give you this one. See if I can move this over. Oh, I don't know what I just did. Hold on, y'all. Can I drag it? Well, they have here, nope, of course, it's not letting me drag it over. Why not? Why won't you let me drag you? I wonder if I can drag this. Nope, okay. Well, this is saying that the Gaussian surface is E naught A, and we know that the area here for a cylinder is 2 pi r, which is the circumference of, see if I can close that part, which is the circumference of that, right? 2 pi r times the length, which is where they were getting that. So since that's 2 pi r times the length, where'd it go? Cylinder, cylinder, cylinder. Here it is. And that is Q inside, which is lambda times length, over E naught. And when you rearrange it, you get that the electric field is lambda over 2 pi E naught R. And since K is 1 over 4 pi E naught, that's where they're getting 2 Ke naught. Ke. This 2 Ke is the same thing as 1 over 2 pi E naught. And that came from Gauss's law. So we've plugged in the electric field for a cylinder here. We say negative 2 K lambda over R dr. When you integrate that, the integral of dr over R is ln. So it became ln of B minus A, and then it was ln B minus ln of A, which then is ln of B over A. And so when you plug that in for your delta V here into your capacitance, capacitance is charge divided by delta V. We also plugged in for lambda is Q over L. And clean it up and you get this. For a spherical capacitor, this one's actually a little easier, I think. Spherical capacitor, your change of voltage from this inner radius to the outer radius is negative E ds, which is negative E dr. And we know that the electric field for a point charge or a sphere is kq over r squared. So that's where we're getting the kq, and they put the r squared down here. When you actually perform the integration, that becomes 1 over r from b to a. So it's kq 1 over b minus 1 over a. There was a negative in here, but there was a negative here, which is why there's not a negative there. That's where they get the b over the a. And then they found a common denominator and put it all together there. When you plug that difference of voltage into your capacitance formula, C is equal to Q over delta V, again, this is a ratio here, then you get Q, this Q cancels out. It's Q over KEQ A minus B over AB. And the reason this is now B minus A is because the capacitance doesn't care if it's positive or negative. The capacitance is always defined as a positive value, and B was greater than A. So if we want to give the capacitance a positive value, it's B minus A. This came from A minus B just because the electric field actually did have a direction to it, but the capacitance does not. So that's why we switched it, to make it positive. All right, last topic for the second section of the E&M example. It would be dielectrics. Let's see if I can. Dielectrics, we've already done that, done that. A dielectric is basically going to be an insulator or a non-conducting material that's placed between the conductors of a capacitor. And the dielectric constant is this K value. It's not the same thing as that KE. It's a different one. And so the difference in voltage that can be established across a dielectric is going to be the original difference in voltage divided by the dielectric constant, which also means that the capacitance would be K times the original capacitance. So the advantages of a dielectric constant, or adding a dielectric to a capacitor, is that you can develop more potential. You can increase the capacitance, which also means that it can operate at a larger maximum voltage because you can have a greater ratio of charge to voltage. Here we go. Dielectric provides the following advantages: increase in capacitance, increase in maximum operating voltage, and then also because it is literally something, it is a material between the two conducting plates, which have opposite charges. You can actually bring the two conducting plates with opposite charges closer to each other without them actually touching because of their attractive force. And by decreasing D, you also increase C, the capacitance. This is actually a pretty good statement. For all problems in which a capacitor is modified by insertion of a dielectric, for example, you must note whether the modifications to the capacitor are being made while the capacitor is connected to a battery or after it is disconnected. If the capacitor remains connected to the battery, the voltage across the capacitor necessarily would remain the same. There's no way to change the voltage because you didn't change the charge. If you disconnect the capacitor from the battery before making any modifications, the capacitor is an isolated system for electric charge, and its charge remains the same, but its change of voltage may go up. But if it was with the same battery, it had to be the same voltage there. Oh, that was pretty cool. That was talking about that's how a stud finder works, because it recognizes the wood behind there. And we're going to skip that right now. Yeah. I might come back to this one. Oh, the basic atomic description of a dielectric is that all of the molecules line up with like positive, negative, positive, negative, positive, negative. And so it's like putting a bunch of little capacitors back to back, which is why you increase the capacitance. Right there. It's like having a bunch of capacitors in series. And that is it for different shapes of capacitors and